Good afternoon, everyone, and welcome to this virtual briefing on advanced chemical recycling. My name is Leela Duman, and I'm the Science Policy Fellow at the American Chemical Society. For those of you who are unfamiliar with ACS, we are a congressionally chartered, not-for-profit scientific society representing over 150,000 chemists and chemical engineers worldwide. This webinar is a part of the ACS Science and the Congress project, which aims to educate and inform members of Congress and their staffs on the importance of science and technology to solving national challenges. The presentations and conversation you will hear today are being recorded and will be made available on our website for your future reference. Today, our panel of experts will be discussing the role that advanced chemical recycling can play in addressing the growing plastics problem. Our three panelists will begin the webinar with short presentations, after which we will transition into a Q&A discussion with you, the audience. Next slide, please. To submit your questions, please use the Q&A feature at the bottom of your Zoom window. If you are joining us by phone, you may email your questions to science_congress@acs.org. We will be monitoring the questions submitted throughout the webinar and hope to have time for our panel to answer as many of them as possible. Next slide, please. It's now my pleasure to introduce you to our moderator for the day, Dr. Catherine Beers, leader of the Polymers and Complex Fluids Group in the Materials Science and Engineering Division of the National Institute of Standards and Technology. Dr. Beers is currently on assignment developing a circular economy program for NIST, where she is engaging the campus in activities related to plastics recycling, new materials design, and the environmental impact of plastic waste. With that, I'll turn the floor over to Dr. Beers.
Thank you, Leila. And I'd like to also extend my welcome and thank you all for joining us today and this critical time for plastic waste, not only in the United States, but around the world. There are two major challenges confronting the plastics industry today. One is a major disruption in global trade, which is really a reflection of the need for a disruption in technology for handling plastic waste. The second is the increasing awareness of the impacts of unmanaged plastic waste, specifically its persistence in and impacts on our environment and health. So this has prompted a lot of focus from industry, government, and academic groups, all taking a closer look at our existing systems and how they can be improved. And specifically today, we're going to focus on the topic of advanced chemical recycling. We have an outstanding set of panelists for you today, so I want to go ahead and get started as soon as we can so we can get to some questions and some good discussion. Our first speaker is Professor Eric Beckman, the Bevier Distinguished Service Professor at the University of Pittsburgh. Professor Beckman was recipient of the Presidential Green Chemistry Award, and his research group examines the use of molecular design to solve problems in green engineering and in the design of materials for use in tissue engineering. He created the Mascaro Center for Sustainable Innovation at the University of Pittsburgh, a school which examines the design of more sustainable products and infrastructure. He has published over 200 papers and received over 40 patents. Professor Beckman, take it away.
Thanks, Kate. If we can have, perfect. I'm going to talk to you all today about chemical recycling, basically where we at in dealing with today's polymers. Next slide, please. I'm going to focus my little talk today on what I call the big seven. Seven basically plastic categories that make up over 90% of the annual global volume of polymeric materials produced. I've lumped them into three categories. The polyolefins, as shown on the slide, they're all chemical cousins to one another. PVC and polystyrene, they're cousins a little bit more distantly removed. And then PET and polyurethane, which I also see as chemical cousins. And again, they're over 90% of the plastic material produced. Next slide, please. Okay, so we can take those seven polymers and kind of, again, break them into two really rough categories. There's those where we've taken a monomer A, and to make the polymer, we've strung all the A's together. So you get like a poly A. And that's the polyolefins, polystyrene, and PVC. Or in the case of PET, polyester, and polyurethanes, it's an alternating situation where we have a B and a C and a B and a C, and we've strung them together that way. Next slide, please. So for chemical recycling, rather than stringing things together, we're actually trying to break them apart. So we start with the polymer chains, and our goal is to either create monomers, which we can then reuse to make other polymers, that would be great, or fragments that we can actually transform to monomers, that would be fine, or fragments that we could just sell as high value products, that would be good too. The one thing that I don't include in chemical recycling is simply creating hydrocarbons that you can burn as a fuel. To me, that's not a good solution to recycling since, okay, it reduces our landfill issue, but then it sends CO2 up into the atmosphere, so not a good choice. Next slide, please. Okay, so to be successful at chemical recycling, first, we actually have to fragment the polymer in a predictive way. So we've got to generate fragments. Second, though, all plastics are mixtures. They're never just the pure polymer molecules. They come with dyes and pigments and fillers and flame retardants and stabilizers and you name it. So we have to be able to separate these fragments we've produced from all of the additives if we want to reuse them. Next slide, please. And then finally, sometimes we either accidentally produce multiple kinds of fragments because our chemistry is not 100% efficient, or in the BCBC type of materials like PET polyester or polyurethane, we're going to get two kinds of fragments. So then we have to separate the fragments from each other. So the bottom line here is that this is not just a chemistry problem, but it's also a separations problem. And sometimes the separations issues can be more complicated than the chemistry. Next slide. Okay, so now a quick update on where we're at with all of these things. So this is PET polyester. It's the way I think about it. You take one of the blue circles and you react with the brown. And when you're making the polymer, every time you react a blue with a brown, you get one molecule of methanol that comes off. And so to push the reaction to make polymer, you have to keep stripping methanol out of the reaction. And a big part of a PET polyester plant is really devoted to getting rid of the methanol. In other words, to drive the reaction to big, long chains. So of course, if we want to go the other way, based on this sort of chemistry, we add methanol and heat, and this will go backwards to go from chains to the blue and the brown circles. And that's been known for many decades. And there are some older players in this field and some newer players that are doing this. The real issue here is that this is the easiest material to chemically recycle, but there's probably the least demand for chemical recycling with this material because you can separate PET polyester pretty easily from other things in a MRF, a materials recycling facility. And there's strong demand from a variety of industries to get this recycled PET flake. Next slide. Now, by contrast, we have polystyrene. Thanks to work by Lanny Schmidt and colleagues dating back 10 years ago and more, folks have known that you can take polystyrene and under the right conditions of temperature and catalyst, you can get back mostly styrene, which is exactly what we want. And there's been some companies of late, Agilix is one, Ineos is another, that have taken processes to depolymerize polystyrene to pilot scale. The issue here is that polystyrene is not normally collected by municipalities. It's not one of those plastics that you're asked to put in your recycling bin. And expanded polystyrene, the foamed analog, no one wants that because then you're transporting around mostly air and it's really inefficient. So we have a logistics issue here. So if Ineos and Agilix can take their technology to the next stage, still got to find a way to get the polystyrene to them so it can be broken down and the styrene reused. Next slide. Then there are polyurethanes, which they have issues, not always of their own making, I guess. So they're one of those alternating things where we have blue circles and green circles, and they're all linked together to make polyurethanes. Now, unlike PET, polyester, where we have one kind of blue and one kind of green, in polyurethanes, well, we have 2 or 3 different kinds of green circles that are used commonly, and dozens of different kinds of blues. So that polyurethane is really a generic term. It describes a whole family of things. So yes, we can get the polymer to fall apart if you add heat. The trouble is now you have this massive separations issue because you have different kinds of greens and different kinds of blues. It's very complex. In addition, once you get the polymer to fall apart, the greens have this awful tendency to then react with themselves in a reaction you don't want to form this weird low volume fragment. Finally, polyurethanes are not typically collected by municipalities because they're usually in long-term applications, like the insulation in your house, your furniture, your car seats, your mattresses. So getting them back to a chemical recycler is, again, not straightforward, in addition to the chemistry and separations issue. Next slide. Then there's PVC, which frankly doesn't work at all in this. PVC, if you heat it up, starts producing hydrochloric acid, not a good thing, which then leads to further decomposition of the polymer, ultimately creating an assortment of hydrocarbon fragments that essentially have no value. PVC has been known to be thermally unstable in this way for as long as I've been alive and longer. So it's just not a good candidate for chemical recycling. Next. That brings me to the polyolefins, which should be ideal for chemical recycling because they're actually very challenging for MRFs. Yes, there are 3 kinds of polyolefins generally, HDPE, LDPE, and polypropylene. But there are many different grades of resin, there are many different manufacturers, there are loads of different additive packages, besides lots of different colors. And so doing all that separation is very challenging for a MRF. And so if we can actually crack polyolefins down to their monomers, then anyone could reuse anyone's polyethylene, and that would be great. So right now, what folks have been looking at is mostly pyrolysis, and this is where you heat something up in the absence of oxygen. Normally, when you do that, you get a fairly complex mixture, and that is in itself a problem, in which you have some gases, which have low value, some solid, which generally that's waste, and then liquids. And within the liquids, there's also a mixture in which parts of the liquid stream are actually valuable. Light olefins, those are actually monomers from which you can make additional polyolefins, so those are good. And then naphtha, those are carbon chains, which right now we use naphtha to make light olefins. So if we could direct chemical recycling to make either naphtha or light olefins or both, this would be golden. Next slide, please. So Lopez and company reviewed the field in 2017 and looked at dozens and dozens of scientific studies dating back 20 years before them and found a couple of examples, very few, that were really intriguing, in which the work that was published showed that they could produce primarily light olefins, which are the monomers to make polyolefins. And that's what you really want. However, none of this work has been scaled up to date because of difficult process conditions or complex equipment. Next slide, please. But people are still working on it. This is a very rich field for work. This is an example that came out a month ago, in which a group created a catalyst which kind of mimics an enzyme in the way it works. They used hydrogen plus this catalyst to chop up polyethylene, and they got 35% of so-called heavy naphtha, which might have value. Now it's got issues. Using hydrogen's not the best. It took a long time, and 35% yield of heavy naphtha is not great, but it's intriguing. Next slide, please. So my summary is that polyolefins should be our key target for research in chemical recycling. It would be great if we could chemically recycle these things. Some of the others, PET is doable, but the demand isn't as good as we'd like. PVC, you can forget about it. And the others are in varying stages. So like I said, in summary, polyolefins, more than half of what's produced, and where I think chemical recycling could have its greatest benefit, but we're just not there yet. Thanks very much.
Great, thanks, Eric. Our next speaker is Dr. Greg Beckham, who is a senior research fellow and a group leader at the National Renewable Energy Laboratory in Golden, Colorado. He currently leads and works with an interdisciplinary team at NREL on the development of green processes and products in the areas of biomass conversion and plastics upcycling. Take it away, Greg.
Great, thanks, Kate. So, Brandy, if you can go to the next slide, please. So what I wanted to sort of talk about today is, it follows on, and thank you, Eric, for the really nice setup in terms of introducing chemical recycling. What I wanted to talk today about was really focused on sort of, again, echoing and hopefully adding to what Eric was noting, realistic challenges and the need for analysis and energy, economics, and environmental impacts sort of perspective when we start thinking about new chemical recycling technologies. And sort of to frame that, I thought first I would talk a little bit about sort of what the ecosystem of plastics recycling and upcycling is. And so today, when, especially in the post-consumer context for waste plastics, mechanical recycling and a materials recovery facility, or MRF, is the main recycling approach that we employ. And there are a lot of benefits to doing this. You keep polymers as polymers, which is nice, and it's certainly applicable, as Eric said, for example, to PET flake from bottles, single-use beverage bottles, but it's definitely not a one-size-fits-all and not universally applicable to many synthetic polymers that we make today, including things like packaging in many cases, like multi-layer film-based packaging, which is a massive utilizer of synthetic polymers, to textiles, to construction waste, tires, coatings, and many more. And therefore, it offers, I would say, reduced incentive for waste plastics reclamation. If you click one forward on the animation, please, Brandon. And this brings us to, you know, advanced chemical recycling and other solutions sort of in the sphere of going beyond mechanical recycling. Certainly, you know, in terms of dealing with today's plastics, we have to, of course, think about expanded collection and improved sorting. But there are other solutions sort of beyond that, beyond mechanical recycling, including the use of solvents to selectively remove one polymer from a mixture of others that certainly I think are quite useful and in some cases already being scaled. Eric mentioned energy recovery, pyrolysis, and gasification as strategies to really take a big sledgehammer figuratively and break plastics down to small molecule building blocks. And then sort of beyond all of those, really the advanced chemical recycling, wherein we're using more selective and hopefully scalable catalytic solutions and even biological solutions to be able to break down plastics to building blocks is sort of really on the forefront of where we're at today. I think it's also important for us to keep in mind that, you know, we have the big plastics today. Eric mentioned them as well, you know, but we have to think about, you know, given bio-based feedstocks coming in and sort of going beyond petroleum, we can also think about using new bio-based building blocks as new monomers for redesigned plastics that are also more inherently recyclable by design. So to me, this field is really broken into, we must deal with today's plastics and we must redesign tomorrow's plastics. If you go to the next slide, please, Brandy. And so, but sort of really focusing in on advanced chemical recycling and dealing with today's plastics, there's two versions of this in my mind, sort of. One is closed loop recycling, and that is you take, and you can see sort of in the very middle, if you follow from left to right, from bottle to bottle. Closed loop recycling is you take a bottle, in this case is the example, you use chemical recycling to break that down to its building blocks, and you reconstitute it back into exactly the same material that it was before. But there are open loop recycling strategies as well. And so one can envision, and then this is where a lot of, I think, creativity and a lot of excitement is how do we break down, say, a single-use beverage bottle that's PET and upcycle it into something that will last 50 years and is much higher value, and be able to perhaps create incentive for waste plastics reclamation at a higher rate than we currently have. And certainly there are many examples already for, again, in the PET case of downcycling, wherein we take, for example, PET flake from bottles and we convert that into textiles. Those still ultimately end up in the landfill. But I think, again, this is sort of the context from a process perspective that I think of when I think of recycling strategies. If you go to the next slide, please. And so, and again, this is echoing comments made previously, but plastics are not monolithic substrates. There's no such thing as just polyethylene, or if it is, it's typically made in a lab by people like Kate, and those are used as model substrates. But the polyethylene or the PET or polypropylene that we encounter sort of in the wild as consumers and is used, you know, are used for marketed products, tend to have lots of other things in them. And even just these single-use beverage bottles shown here have PET as the primary plastic in the actual bottle component itself. It has polypropylene cap. It has a label on it, which can be all manner of polyolefins or even other types of materials. And it's got co-monomers in the PET. It has colorants in it to not look yellow, essentially. It has the polymerization catalyst many times in there as well, and stabilizers, antioxidants, and much more. And so there's no such thing as monolithic plastics. And so when we think about advanced chemical recycling solutions, to make them real, we have to be considering all of these complexities therein. If you go to the next slide, please. And I think the other thing too that, in the popular press and very much justifiably, we think of plastics and waste plastics specifically as an environmental problem. It absolutely is a dire environmental problem, the extent of which we are, I think, still just discovering. And however, it's also an energy problem to me. The sort of top line note here on this slide is likely very obvious, but plastics manufacturing, sort of shown in this Sankey diagram from this very famous Geyer et al. Study in units of millions of metric tons. This was sort of primary production of plastics, so 8 billion metric tons of plastics at the time, produced as of 2014 or so, more than half of which have been discarded. This requires energy and emits greenhouse gas emissions. And to think about advanced chemical recycling solutions, we need to be considering this as an energy, economic, and environmental impact problem when we think about waste plastics. And if we want to enable circularity, we have to think about, are our technologies that go on the bottom darker blue sort of circle there more energy efficient than virgin production? So if you go to the next slide, please. And so when we come up with ideas, for example, this is sort of this cartoon shown here of, for example, using enzymes with synthetic polymers like polyesters. We can use enzymes to break them down. We have to think about this not only from, the really fun science and really exciting research that we can do studying and making better enzymes and making them faster, but also thinking about this process at scale. What would the economics look like if we did closed loop recycling, for example, of polyester from textiles? We have to think about the economics, the energy relative to virgin PET manufacturing in this case, as well as the environmental impacts that those would create. And there are engineering and chemical engineering tools, of course, to do that, and life cycle assessment tools to do that, but we absolutely have to be using them in these contexts. So if you go to the next slide. What we're showing here, this is the top 18 plastics that are produced at 1 million metric tons per year or greater globally. And what we've done in this case, for example, is estimated in red the amount of manufacturing energy and in blue the amount of GHG emissions for all of these commodity plastics that are consumed in the US, and in green is shown the US consumption. And so to me, these are really important baseline data, because this says to make these products, you need to be able to, implement advanced chemical recycling, we need to have lower energy input and lower GHG emissions, as well as economic incentives towards being able to essentially beat or match at least these types of linear incumbent technologies. And so if you go to the next slide, please. This is my last slide. And so I wanted to highlight a few key opportunities. I will actually perhaps make a counterpoint a bit to Eric. Polyolefins certainly are the biggest fish out there, polyethylene and polypropylene, but there are many other plastics that are not recycled today. And to me, those are very important targets to go after. Biomass and waste, including discarded plastics, of course, also offers new building blocks for redesigning tomorrow's plastics. I think we also have to keep that in mind. In terms of key needs, certainly I've talked a lot about, but can't stress enough, energy, economic, and environmental analysis methods are important here. And the bottom line is we must develop technologies that offer net positive gains in all of those categories. So thank you. That's what I have. I'll turn it back to you, Kate. Yeah, thanks.
Great, thanks, Greg. And I'd like to remind our audience that if you have questions or concerns you'd like to express that we can address, please post them in the Q&A function of your Zoom browser or Zoom tool along the bottom of your screen. Our final speaker and panelist is Dr. Jill Martin. She's a fellow in the packaging and specialty plastics business of the Dow Chemical Company. Her current role is aligned in developing plastics for a circular economy. And in this role, she has responsibility for development of products and partnerships within the packaging value chains, including the private and public sectors, to enable acceleration of scalable solutions. Jill?
Thanks, Kate. Appreciate the introduction. You can see by the title here that I've used the term advanced recycling. I think you heard Eric and Greg call it chemical recycling, and we usually use the term advanced recycling to distinguish it from mechanical recycling, but to be inclusive of processes that not only create building blocks, but also look at potentially dissolution processes. The other point I want to highlight here on this slide is that we're really thinking about a circular economy. Many people are aware of the distinguishing factors differs between a linear and a circular economy. I think it's important that as we're talking through these various challenges in front of us and the various, again, solutions that are being proposed, that we think about it in that broader context of how those solutions actually support and grow our economy, not just for plastics, but for all materials and waste. Next slide, please. I'm going to start by actually talking a little bit about the waste hierarchy, and Greg touched on this in his last slide, which is really looking at what are these waste streams actually doing in the country today. And the EPA put together this waste hierarchy quite a number of years ago to really talk about the fact that there's no single solution for all the materials in all the geographies. And if you manage waste on a local basis as part of a municipality, you know how important it is to be conscious of the community's own habits in terms of waste management. The hierarchy also looks at a least preferred route, which of course is treatment and disposal, and looks at those most preferred routes, which would be associated with both source reduction as well as reuse of those materials. Effective waste management strategies really are going to be emphasizing recycling and reuse and reduction of materials, which we typically think about in the packaging spaces, down gauging and lightweighting. However, the challenge is that, quite frankly, the plastics recycling rate, in particular those of high-density polyethylene and PET, have been stagnant in the US for the past 10 years at about the 30% level. Part of this is driven by the fact that there are markets that have basically not necessarily adopted the use of these materials, but it's also, quite frankly, a reflection of the fact that we don't have a uniform standard for collecting and sorting and actually classifying those materials. So in the US, we tend to be more dependent on both landfill and energy recovery or waste to energy for those harder to recycle materials, including flexible plastic packaging. The answers are some that Eric and Greg have already touched a little bit about. Technologies that we're talking about are not only those that are in the advanced recycling bucket, but also in mechanical recycling, taking again quality of materials to higher and higher levels. We're expecting growth rates for a number of these technologies to be as high as 17%. And this balanced approach will really enable a transformation of the systems that are in place today to reuse and recycle those harder to recycle materials, including multi-layer flexible packaging. Next slide, please. So if we look at advanced recycling, again, in terms of why is it going to be differentiated from other recycling technologies that are out there today, there are 3 points that I want to talk about. The first is really coming back to the quality of the materials that you can make. And as we've touched on before, because polymers and the articles from which they're into which they're made are actually not just composed of macromolecules, but also other additives, we obviously have to look at how do you get rid of those materials in order to get back to just the molecules and to build new materials. Advanced recycling technologies can typically get you to exactly the same type of performance that you would get if you were to use fossil fuel-based sources, and this is a strong selling point for those materials because it also enables you to use those in applications that mechanically recycled materials cannot be used in today. The second point is that it allows you to source a broader source of the waste materials than we are talking about traditionally. So we're not looking only at monomaterial streams, we're looking again at multi-material streams. This could also include organic waste. And so the idea of actually taking municipal solid waste back into some of these advanced recycling systems, in addition to the plastic waste, is certainly on the table for discussion. Again, a way for us to manage not only the landfill, that's the organic component, but also the inorganic component. I think part of the other option here that's on the table, or one of the advantages that's on the table, of course, is the ability for these materials to be used in food contact applications. And I think many of you are aware of the fact that today the FDA regulates what materials can be used in food contact applications. And a couple of the streams that are available that are based on high density and PET can be used in food contact applications. And so the FDA has issued a letter of no objection for those materials to be used, again, back into consumer-facing segments such as food. However, not all of those PCR streams that are available today have that type of a compliance, and it is expected that many of the advanced recycling technologies will deliver on food contact compliant materials, which expands the market for post-consumer recycling. Next slide, please. Of course, there are multiple challenges which need to be overcome. And Eric and Greg have already talked a little bit about those. Of course, when we're talking about technology, we're talking about the learning period associated for any new processes that are brought into the marketplace today. That will take a couple of years. Obviously, optimization for those supply chains for those technologies will be critical as well. We need to also acknowledge the fact that a lot of the processes we're talking about today will require us to be conscious of the impact from an energy and water utilization. Greg talked on this a little bit with respect to LCA as well as TEA. The economics of many of these processes are not in alignment with processes that have been running for 50 or 60 years, but as we have more and more experience with those processes in the industry, they will become more efficient and the economics will continue to improve. A recent study by the Closed Loop Partners actually called out 64 different projects today that are valued at just over $5 billion that are focused on new mechanical and advanced recycling technologies and the way to implement those technologies across the broader U.S. economic landscape. A variety of policy solutions, such as packaging fees that fix the problem for the long term, can be applied fairly across the materials portfolio and are flexible enough to enable industry to innovate, should also be considered when we think about how we can actually bring a number of these technologies to market. When I talk about collection and sortation, we're not actually talking about a technical problem, we're talking about an infrastructure problem. And this is one where we really think about waste as being a distributed source of materials. It really isn't about the same type of aggregate that we're talking about when we're looking at manufacturing operations, which for the chemical industry tend to be along the Gulf Coast of the US. We're really talking about waste being very much local. So we need to have those capabilities, not only that infrastructure, but also the way to manage the material once it comes into a material recovery facility so that we can provide a consistent waste stream for not only the existing recycling processes, but also the advanced recycling processes. So optimization of that supply chain is obviously very critical for us to move forward. Let's go to the last slide, and I'll talk a little bit about some of the options that we have on the table and the way we're looking at some things that need to happen in order for this to be successful in the long term. We fundamentally believe that plastic is too valuable to go to waste. It's quite a large industry, not only in the US in terms of the number of people it employs, but also the value it creates for the economy. But in order to really accelerate that circular economy, there are 3 points that I'd like to make. First of all, again, coming back to the hypothesis that we're talking about today, and that is that advanced recycling is going to play a critical role in keeping waste out of the environment. But we need to make sure that it's integrated with existing mechanical recycling facilities to minimize the amount of waste that ends up in landfills, but also maximizes the value of the recovered materials so that there can be broader adoption of these materials into markets where they might not be found today. Public policy is a critical enabler for successfully establishing that circular economy that we talked about at the beginning. Policies that include partnerships can help drive that innovation, accelerate the adoption, increase the amount of education for the consumer, and expand the resources that can be put in place to address the plastic waste issue. Advanced recycling technologies are not necessarily just for one single party in the value chain, but they're necessary for industry, for governments, and for research labs in order to help the brand owners and associated customers meet their commitments regarding recyclability and recycled content. So thanks for the attention. And Kate, I will turn it back over to you for Q&A.
Great, thanks, Jill. And thanks to all of our speakers for your great introducing remarks. We're going to move on to the question and answer section. I'd like to remind everybody that there is an option down at the bottom of your screen to add a question or a comment if you have them. The way I'm going to do this, I think the questions will be open to everyone to respond, but I'll let you know before I read the question who I want to speak first so that you aren't caught off guard. So our first question is for Jill. In one of your slides, you said that recycling growth rates are projected to be as high as 17%. Can you explain this number and what this means?
Yep, I apologize, Kate. I was answering your question while I was on mute. So I said all the smart things already. No, but I think that the numbers themselves came from a study that McKinsey did a couple of years ago, really looking at the possibility for not only advanced recycling, but mechanical recycling to really be a part of the overall materials management strategy going forward. So that 17% is reflecting what we're seeing in primarily advanced recycling as far as what we were projecting out into 2050. So again, this is a very forward-looking growth number, but that 17% is inclusive of mechanical recycling as well as advanced recycling technologies.
Eric or Greg, did you have anything you wanted to add to that?
No, this is Eric. No, that was good.
I'm good.
Yep, great. Okay. So the next question is for Greg to start. Should all plastic and polymer waste be fed into advanced and chemical processes? Is there a role? And I think we've spoken about this a little bit in our presentations, but is there a role still for mechanical recycling, perhaps expanding this mechanical recycling as part of this ecosystem-like solution to plastic waste?
Yeah, great question. So certainly advanced chemical recycling is a very broad portfolio of technologies, many of which are still are quite nascent and are still very much in their infancy, and many of which probably haven't even been discovered yet. At the same time, mechanical recycling, where it works, is great in the context that you keep a polymer. To break a polymer down to its building blocks, like Eric showed on his introductory slides, it does take work. It takes energy. It takes, it takes work to do that, and then to build it back up to a polymer also takes work. And so, where mechanical recycling can provide value, where it can create economic incentives for waste reclamation, where it can be expanded and improved, I think it's one of the tools that we have available to us in addition to solvent-based recycling, advanced chemical recycling, energy recovery, pyrolysis, gasification. To me, all of those technologies need to be put on the table, and there's not going to be a single sort of silver bullet solution that will work for all plastics in all places at all times. And so for me, absolutely, it's part of our portfolio that we have to leverage.
Yeah, I think when it comes to the sheer magnitude of the volumes of materials we're talking about, we have so much complexity on the front end of how these materials are produced. I don't think it should be surprising that a really complex set of solutions on the back end is probably going to be the best solution for everybody in that case too. Eric and Jill, did you want to add anything to that?
Yeah, it's interesting, but I think that as more advanced or chemical recycling processes are developed, I think you're going to find more complementarity between traditional mechanical, the sortation part, and chemical recycling. So for example, if some of these polystyrene depolymerization processes make it to big time, go beyond pilot scale, then we're going to need to start collecting polystyrene. And fortunately, polystyrene's chemistry is such that it can be sorted out from other polymers by some of the near infrared scanners that they use in MRFs. So then the two are complementary. We're going to need the MRFs to sort out the polystyrene, which will probably go to a chemical recycling facility and reprocessed. So I think they're actually complementary.
Yeah, I think this is one of the most fascinating approaches, is to really think about, and I think there's some large cities in the US that are starting to think about how you have a single site for waste management, such that, to your point, Eric, something coming out of the MRF might go to a pyrolysis facility, or it might go to mechanical recycling to turn it back into pellets. So again, the idea of integrated waste management facilities would allow, again, that a more efficient transfer of, let's say, waste into value versus, again, shipping it across the country to have something done. So I think there's some very interesting models being proposed at the municipality level that could very well adopt all of the technologies that we're talking about today into a single site.
Yeah, Jill, you did a great job in your talk also of pointing out that while we're talking about this as a national and a global problem, it really starts at a local level, and we have to find ways to support the local municipalities, the states and local governments in how their infrastructure is developed and what kind of technologies are available to them. It's really critical. So our next question, we'll start with Eric, but it's really for the whole panel. What do you see as the best roles for universities, the private sector, and the national labs or other federal research entities?
Wow. Well, some of this field is very new and hence very risky. Before I went into academia, I was in the private sector. And if I told my bosses at the companies I worked for 35 years ago that I wanted to design a polymer that would fall apart on command, they would have had me shot. That's not how you design polymers. Since 2016, though, in academia, that's quite a burgeoning field where you've got a number of academic scientists trying to create things that actually will fall apart on command. The idea being at end of life, it's not as hard to fragment them into usable fragments as might be the case for some of the traditional thermoplastics. So I think the key is that on the academic side, in theory, we should be free to take scientific risks. And in particular, on a field as new as, designing a polymer that will fall apart at end of life chemically with some sort of a command, that's exactly what I think academics should be looking at. I think that the private sector is a lot faster at getting things done. And, they also have, current issues because they have to deal with the material they're producing now. They also tend to take a more systematic approach to things, I think, because they're always dealing with issues of energy use and logistics and supply chain. And so, when I look at some of those aspects, that seems appropriate for them. And the national labs are somewhat in between. Some of the most interesting stuff that I've seen come out has come from national labs because they sort of have a foot in both camps. I mean, one of the first really interesting examples of a thermoset material that you can take backwards and then separate the pieces came out of Lawrence Berkeley. So I think they each have their roles and they're all slightly different, but I think they're all important in this because it's just really new.
Yep. Greg or Jill, do you have anything to add?
To me, I think that this problem is just so multidisciplinary and multifaceted that having folks at the table who do, truly fundamental basic science R&D, but with a nod towards this problem, translational R&D and transparent analyses, both in terms of what is the problem and what is the scale, magnitude of the problem, as well as what are the potential, efficacies of various solutions from energy, economics, and environmental perspectives. All of those things are, roles of universities and national labs, and companies, of course, do all of those things too. And so in enabling sort of connections between those entities in a multidisciplinary way, I think is how we will ultimately solve this problem. And then getting through the valley of death is something where you need to push and to pull. And I think, again, that's where those sort of three bends of entities have to work together to enable it truly scalable advanced chemical recycling solutions.
And just for those,
go ahead. I'm sorry, Kate.
I'm sorry. I wanted to say that for those of you that aren't in the field, the Valley of Death is really that transition point between basic research and innovation and getting things into the marketplace. So it's that level of technology development that has to occur to commercialize technology.
Oh, thanks, Kate. Yeah.
Yeah, I think there might be even two valleys of death, Kate. Certainly there's three different parties involved. One thing that I think that both Greg and Eric touched on as well is the way that we look at those solutions. So for example, when you think about doing the LCA and looking at the impact from an energy and water impact perspective, that I think it is important for each entity in that collaboration to really be speaking the same language and using similar tools. So when we're thinking about, this is not about how we do basic science, it really is about how we identify the solutions that have the highest probability of success at some reasonable scale. And quite often the industry is caught up in this debate around what is the right scale for these solutions. And I think there's actually not an answer when it comes to basically what's the right technology for us to move forward with. I think that there will be, again, technologies of all sorts available, but those might also have different scales. And so we shouldn't necessarily always be caught up in if it's not a big scale, then it won't help solve the problem. I think, again, that flexibility is going to be critical as we're looking at the technologies that are available.
Great, thanks, Jill. Okay, so our next question is going to be, we're going to start with Jill, but it's really for the whole panel again. What ratio of R&D resources are being put toward advanced recycling and other aspects of the circular economy by the private sector. And in parentheses, it says versus other R&D activities.
Well, okay, so I'll answer that not only from my personal perspective, but also from my corporate perspective. So we basically have that as one of our 4 operating principles. One of our value propositions, part of our mission statement, is to be a sustainable material science company. So we have quite a lot of our R&D as well as our manufacturing and engineering teams looking at sustainable processes and sustainable materials. And that transformation has really occurred not just over the past 2 years, but over the past 20 or 25 years. And I would certainly say it's stepped up quite a lot over the past 5 years. It's always been part of what we've looked at, but I would say that absolute ratio between sustainably aligned resources and others has definitely changed. But I think if you say it's part of your company's mission statement, then in essence, everybody has a role. It's just that, again, it might be 10% of your role versus 100% of your role. So maybe I just answer the question from both viewpoints there.
I'm not sure if that's something any of the 3 of us can comment on, not being from the industrial sector, but if anybody has anything else to add, maybe Eric or Greg, you know something about that?
I certainly cannot comment on the ratio of R&D resources, of course,
right.
but I will say on a pretty fun note, at least I think it's fun, the level of engagement from my vantage point from industry to universities and national labs in this space right now is overwhelming in a good way. So yeah, we're definitely getting lots of phone calls these days and emails, which is quite exciting.
Yeah, I completely agree. From my position, I see that as well, which is really encouraging. I think there is a serious recognition and interest in the potential of this market.
Yeah, this is Eric. I don't think this was a field more than 5 years ago, realistically, and now it's grown dramatically. I think the Geyer paper, Jenna Jambek's group's work, really pushed this forward.
Well, and I think the trade disruption also was a big factor. So the China sword and the ability to transport poorly sorted plastics around the world really was a big source too.
Oh, definitely.
Our next question, I'm not sure who the best person is to start with. We'll try maybe Greg. Can you share some context for where the EU and other leaders in this space are investing that would help the US?
Certainly, I think the EU is definitely policy oriented around the advanced chemical recycling space. There are, to my knowledge, which is limited, and probably I'm getting out of my depth here really quickly, but there are certainly investments from some companies scaling up things like pyrolysis and gasification of plastics in the EU towards being able to reintroduce those building blocks into refineries and things like this. I think this goes to Eric's point, right? I think the truly advanced chemical recycling, using more selective approaches for breaking down today's polymers, I would say that is such a brand new field. I mean, it has been looked at for decades, but not in a very earnest and serious way at a very large scale, I should say. And so to me, I think we're all sort of on the cusp here of working on a lot of these things together. So I'm not sure if I'm answering the question, Kate, but that's my 2 cents.
Yeah, it's a tough question. I would say, from my point of view, I think that their regulation posture is certainly more aggressive. I think one of the areas where we see an opportunity to work with them is in the standardization space around labeling and standard measures and documentary standards for trade and certification, that sort of thing. But that's just the uniqueness of my particular organization's mission. I don't know if others see other opportunities.
Maybe I'll speak to this design for recyclability space, where we're seeing a lot of collaboration between the EU and the US in terms of setting guidelines for what is a recyclable package today. And again, very focused here on flexible packaging, but that is extremely helpful for the CPG companies who are looking to standardize packaging structures on a global basis, is to have some direction about what would be considered recyclable. So the EU and the US are working very closely on those, and not necessarily at the government level, but more at the organizational level. So Plastics Recyclers Europe, for example, and CFLEX and other organizations working with APR and ACC, for example, to really better understand what does it mean when we say something's designed for recyclability. And again, that's a materials look, but I think to your point, Kate, it's a good way for us to enable the market to really help decide as well, or have a say in terms of what really should fit within the recycling infrastructure.
Great, thanks. And I think this probably will be our last question. We can start with Eric and go from there. One of the additional aspects of the complexity for recycling, as mentioned, is sorting and multi-layer packages. Is anyone aware of work being done to support separation of polymers from each other in either case?
It's a good question. What I've seen, rather than, I've seen some work on trying to separate things by creating adhesives that will go backwards. An adhesive that you can hit it with a chemical trigger and the adhesive will literally fall apart. This was first applied in the carpeting industry to create carpets that you could basically take apart the three different types of materials in them with an adhesive that goes backwards. So I've seen some work there. More so though, I've seen work on folks trying to reduce the need for multi-layer packaging. In other words, we need multiple layers because just the polymers alone are not good enough to reduce the transmission of oxygen and moisture needed to keep the food fresh. So rather than emphasis on separation, I have seen work done on trying to enhance the properties of the polymeric materials so that you don't need so many layers.
Greg or Jill, did you want to add anything?
I'll very briefly state that, or say that the other area wherein work is very actively ongoing is thinking about when you have multi-layer polymer films. Those polymers, given their differences in chemical identity, will tend to respond to solvents or selective applications of solvents in a different way, such that you can apply, solvents in given orders and be able to pull one out relative to all and leave all the others behind, and then apply it separate. Second solvent, pull one out, leave all the others behind. And so, certainly in that context, there's work ongoing quite actively.
Jill?
No, I don't really have anything to add. I appreciate both of you highlighting, though, the challenges around multi-layer flexible packaging. That's pretty much what we spend 100% of our time on any given day. So I think there's a lot of opportunities there. It really comes back to, though, and those processes, what's the energy intensity associated with that, effective solvent recycling technologies, and, again, trying to make sure that at the end of the day, the quality of those materials is greater than the quality of materials using other processes.
Yeah, I will say that the Department of Energy has recently invested in a new academic center for researching catalytic conversion of multi-laminate films. That's at the University of Delaware. And with regards to sorting of plastics, I know that there's a lot of emerging technologies in robotics and optical sorters and the use of artificial intelligence. We think there's huge opportunities in terms of the training data used for those for AI tools, as well as algorithm development for sorting technologies that could radically improve the quality of our sort across the local municipalities in the country. So there's definitely opportunities there. How many of them are actively being pursued right now versus the early stages of investment, I think is a separate question. Okay, well, I think we're just about finished up. Let's see, do we have time for one more question, do you think? I know we have a time constraint for one of our speakers. We could try to squeeze in one more, or we could just call it a day. What do you guys think?
Okay, one more.
Yeah.
We can squeeze in one more. Yep.
We've got more, which is a sign of a good discussion. So let's try this one, because I know it came up with both Eric and Jill to some extent, and also with Greg, I think. Designing materials to do their job during use and then at the end of life to either fall apart or reprocess easily with non-toxic components sounds great, but difficult. Is it really possible? Should the government make more resources available for research on such smart materials, or do you see this as a task for industry? Who'd like to start with that one?
Ooh, this is Eric. You want me to start that one? I call these orthogonal triggers. When I describe this entire process, what you want is a material that'll go through its normal use span and never encounter the trigger that says, now fall apart. Because if it did, it would fall apart during use. So it has to be a trigger that the material just sort of goes along, it does its job, whether it's in packaging or a child's toy or something, and never sees this trigger. And only when you collect it at the end of life, then you hit it with a trigger. I've got a great example of that. It's a thread, literally a thread used to sew things together, created by a company in Britain that was microwave sensitive. So if you took the garment and put it in a microwave, the thread would fall apart, and then you could take the panels of fabric apart and reuse them. And of course, a garment, unless you had a very naughty child, would never see the inside of a microwave. So that's an example of an orthogonal trigger. And so this sometimes involves new chemistry. And then secondarily, then once you get the thing to fall apart into pieces, then you've got to separate the pieces. And people often forget about the separation side of the problem. There's resources being put into this by the National Science Foundation and the Department of Energy right now. I'm an academic, so my job is to say there's never enough research money out there. But I know, again, over the past 4 or 5 years, this has become a rich area for research, at least in the academic community in the United States. There's been some really good stuff that's come out of both national labs and some universities. It's just because of the orthogonal nature of the triggers, it's really hard, but I think it's doable.
Maybe a comment not on the science, but more on the government role. And we talked a little bit about this before we met today. But thinking about the fact that we've got some very exciting problems in front of us now. And I don't think there's really been, right now in my personal career, more excitement for me in what I'm doing on a day-to-day basis. So if I think about the government in terms of where should they put their resources, obviously in existing programs, but I think it's also important to invest in STEM programs for the chemists and engineers of the future, because the generation behind us is very passionate about these problems. And if we are bringing them in an early stage and funding research opportunities for people in the high school level, I think that brings those new ideas, the fresh ideas, the different perspectives that we'll need. So that's the way I'm looking at government resources, not on just particular problems, but making sure that we have the problem solvers of the future ready to go.
I completely agree. I find it extremely easy to motivate creative problem solving in this space with many of our scientists across multiple disciplines. So I couldn't agree more.
Oh, absolutely.
Agreed.
Getting
grad students to sign up for your group when they're working on this sort of a problem is a piece of cake.
Absolutely.
No problem. Right. Same thing with Endow. Yep.
Yeah. Exciting future to look forward to and a lot of good work to do. So with that, I would love to thank our speakers for participating in our panel discussion today. I'd like to thank the audience for attending. I'd like to remind everybody that this presentation, this entire hour, has been recorded and will be posted on the ACS website shortly. And if you want to follow up with anything, we encourage you to reach out at science_congress@acs.org, where they can take your questions, comments, and feedback, or connect you to anyone else. Thanks for your time today, and enjoy the rest of your afternoon, everybody. Stay safe.